You will remember that we said in the beginning of the semester, we had a discussion about order of execution and program efficiency, speed with which an algorithm executes. And then we had a discussion on order n square, order n log n, etc., and which is best. And of course, order n square is bad. And order n is okay. Order log n is better still. Think about a finding of data in a list. If we want to find an element in a list of data, and I do a sequential search, in other words, comparing my element that I'm looking for one by one, and worst case scenario would be that I would have to travel through all elements in the list. And if there are n elements in the list, I will have to compare n elements, worst case scenario. And then we said, but we can do a binary search. But the binary search has this condition, that the elements in the list must be sorted. And then if I know that the elements in the list are sorted, I can aim for the middle and compare my element that I'm looking for the one in the middle of the list, and then determine if I have to go forward or backward. And once I've determined that, I can split the remainder of the list in half again and aim for that one. And then again, determine if I want to go forward or backward. And in this way, I can make the remaining part smaller and smaller and smaller, reduce the number of elements that I have to look at. And we said that worst case scenario will now be log n base 2. So that if I have 1,000 elements in my list, and we know that 2 to the power of n is 1024. So if I have 1,000 elements in my list, and the list is sorted, I will never have to compare more than 10 elements before I get to the one that I'm looking for. That's binary search, and it's efficient. But we can do even better. And that's where hash tables comes in. We can do even better. We can do order 1. Order 1 means immediately. Order 1 means immediately. Order 1 means I know where the thing is and I just go there. I don't search for it. So it's constant, and the search time does not depend on the number of elements in the list. No n in the expression. We just go there. You know where to go, you go there. It's like in the older days when we still made use of the post office. There's this wall of post boxes, and they're all numbered. You know your number. You don't go search, not even binary. You walk up to the post box and you open it because you know the number. You know where it is. That's order 1. So that's what this chapter is about. Dictionaries and hash tables. So before we get to hash tables, let's just understand the basics of dictionaries. I got a question Friday, I think. Where's Mr. Ntivana? Yes, sir. Thank you for the question. What is a key value pair, sir? Because there's a key value pair in the assignment that you had to do for today. Well, it's just what its name says. It's a pair of values consisting of actually 2 values, a key and a value. As in a normal dictionary, let's say we have a Sesotho English dictionary or English Sesotho. And I'm an English speaker and I want to learn Sesotho. So what I do, I want to look for a specific name on the English side. Can do a binary search, find the name, find the word, and then next to it will be the Sesotho equivalent. So the key will then be the English frame, English word, the thing that I want to look for on the key side, on the lemma side. And then on the value side, I will have the Sesotho equivalent. So a dictionary has a list of key value pairs. So when we write that in code, we write list, angular bracket, key value pair, angular bracket, string, string, close angular bracket, close angular bracket. You got it? So it's a nested thing. List, key value pair, type, type. Right. The two types that we indicate in our key value pair are the types of the key and the value respectively. First one will be the key, second one will be the value. So we need to understand what a key value pair is. In the example that I have, I did not make use of a key value pair, I developed a struct. So instead of having a key value pair, we can have a struct. That's exactly the same thing. But instead of making use of the built-in key value pair construct that's available in .NET, I make use of a struct where I define my key and the value separately. And I have also a constructor there that I can use to instantiate and initialize my key and value. So that's just the same thing. So now I have a list of entry in my dictionary. So we have to understand what the key value pair is, and we have to understand what a dictionary is in basic terms. So in the example further on, I say, all right, let's take a file with data. And I use a text file with data of a dictionary. And let's open that so that we can see how the original thing looks like. Let me just go there. Sorry, I should have opened this before. Dictionary.txt. So that's our dictionary. So it's a tab separated thing. So on the left hand side, this is an Afrikaans English dictionary. So on the left hand side, we have the Afrikaans entry. And on the right hand side, we have the English equivalent. And you will see that the Afrikaans entries are sorted alphabetically. I think there's 13,000. It's a small dictionary. There's 13,000 odd entries in it. All right, so we make use of add entries method that will take the values from the file and enter it into the dictionary. So in this example, we have several types of dictionaries and hash tables, all of them in one simple example. So for the test or exam or when you study, you can focus on this example only. All the possibilities are in this example, and they are all now at the top called from the main method, and then we just call them one at a time. So what I also do in this example, I have a timer, and then that timer will start and stop, and we have a time. Now, we time two things. We time the time that it takes to generate my dictionary structure and the time that it takes to find the value in the dictionary structure. And you will find that in some of the possible ways of doing this, the time to generate the dictionary is quick, but to find the value is fast. And the time may be other way around. Maybe we can take a long time to generate the dictionary, and then finding it will be fast. Ideally, we would like to have a structure where we can generate our dictionary quickly and also find the value quickly. So the efficiency of both of these operations must be quick. So I have here several examples. examples. Normal array with linear search, normal array with binary search, .NET list, .NET dictionary, etc., etc. They're all there listed. And then in my main method, I call all of them, the one after the other. And when I run the main method, that's what I get. All the examples, I've numbered them 1 to 8. And in brackets, we have the paragraph in the tutorial that corresponds with the discussion. So we can see then that for each one of those, we have the 2 times. We have a time to add the elements into the dictionary and a time to find a specific element in the dictionary. And I have a specific example test case. I find the word pieperig. You know that word? Sesotho speaking people? English speaking people, do you know it? I don't know what it is. I idiomatically translate it, but there's a lot of possibilities listed. Squeaky, piping, weakly, sickly, soft, etc. All right. So I find the word pieperig in my dictionary. And of course, I can try to find other words as well. Every time that I run this, I will get different times. It's not exactly the same, but the order will be the same. And every time that I run this with maybe a different example, I might get a different result. But the order will be the same. Yes, sir. We will get there, sir. We will get there. Don't preempt things. We will get there. That's one of the disadvantages of some of the structures. But we will get there. Don't worry. So I just give you the basic overview. So there are 13,800 plus entries in the dictionary. And if I do it with a normal sequential search, that's the time to read through the data in the text file. And then if I want to find a specific value, that's the time that it takes to find that value. So the algorithm to find, sorry, let's just go to our dictionary. It's normal file read. I have an array, and I have an array index. And for each one of my entries in the dictionary, I split with a tab. And the first one, index 0, will be the key. And the second one, index 1, will be the value. And I use my entry struct that I've shown you constructor with the key and the value. And of course, I could have used the key value pair. No difference, Mr. Ntuvana. And assign it to a specific index in my array. That's all. And then I just resize my array again to get rid of the extras, because I think initially when I generated this thing, I generated it with 200,000 spots, but there were only 13,000 odd elements. So I just remove all of the others so that the dictionary is not taking up unnecessary space. So, and then I have my timer and start and stop for the add entries method. And that MS add entries, I will just keep a temporary copy so that I will be able to write it down there in my write line statement. And then I start my timer again and do a search for a specific value and stop my timer. And then at that stage, I have my MS duration for the timer. That is the time for the search. Now I do a sequential search. And note the sequential search. I know that worst case will be N, but we don't have to go to the end of the array. If something is early in the array and I found it, it's no need to carry on to the end. I can just as well stop when I found it. So I have that flag there. And I compare every entry in my array with index I with the key that I want to find, the thing that I defined as my search string as a constant at the top of my program up there. All right, so, and once I found it, I stop the timer and I display. So that's sequential. Go through the data one at a time. If, on the other hand, I do a binary search, entering the data will be the same as for the previous one. But then I have to sort my data, and that's important. For the binary search, I have to import, I have to sort. So what I do here to sort, could have used one of our known sorting algorithms, but I decided to, instead of that, take this array that I have entered my dictionary in, feed this to a list, then use the list order by method, and then create a new array by just using this toArray method there. So this sorting will take a lot of time. So if I run, just compare the first two entries. Just compare the first two entries. So normal search, time to add, 41 milliseconds. Binary search, 88 milliseconds. So that takes longer, but that's because of the sorting. Time to find, that's linear. Time to find, so you can see the big advantage that we have to find an element if we do a binary search. Big advantage. But the drawback is that you have to sort your data. If you generate your dictionary once only, and you know that you will generate it once and use it often thereafter, then it justifies the time that it takes to sort. But if you generate once and only search for something once, then it might not justify. So it depends on your scenario, whether you want to use a linear or a binary search. If I go with .NET built-in methods, so let's say I use a .NET built-in list. Again, the add entries method this time looks a bit different, as it now makes use of the add method. It does not have an array, I have a list, and I add data as I go to my list. And once I have the data in my list and I do a search, I can use the built-in find method. And you might think that the built-in .NET list will be quick because it's a built-in thing, and the Microsoft people would have done it as efficient as possible. Well, surprise. If we look at the feedback here, time to add is not that bad, but the time to find is even worse than our own linear search. Actually, link is not efficient in general. Link is okay because it's a extension class, and you know what extension classes are. It's an extension class on the .NET built-in list. But link in general is not good as far as efficiency is concerned. It's just convenient because it shortens our code, makes code writing a bit easier. But in general, link is not good, and you can Google that as well, and you will find that that is true. Link is not an efficient way of dealing with data. You can do better, but it's good to have. It's convenient. All right, so that find, built-in find method with link, we say, is bad. So the next possibility will be go to a balanced tree. Now you will remember what a balanced tree is. Do you? I mentioned it last week, or the week before. Yeah, the week before. At the end of our chapter of trees, I said that this is for enrichment, and you should read this. And there was a section on balanced trees, AVL trees and red-black trees, etc. And just take a step back. You remember that we said a good tree is a shallow but broad one. The bad tree is a deep one. And if the initial data that we add into a tree is sorted, we will end up with an unbalanced deep tree, so that when we search through the tree, it's as good as we search linearly. You remember that? So if the initial data is unsorted and the data is added so that we end up with and the people online cannot see me dancing up in front of the class, né? But you see, and you know what I mean. So that's the advantage of attending class. So if we end up with a balanced tree, the searching will be faster. Now, if we have an unbalanced tree, and I want to make sure that it is balanced, there are algorithms to do so. So take the unbalanced long linear tree, and I'm showing here to the people in the class, those of you who don't see me, a long linear unbalanced tree. And I want to make this thing balanced, then I can apply an algorithm, which I said is not for exam purposes, for enrichment. Now that algorithm is what is used in this .NET sorted dictionary class. That is what is used here. So we add data to my dictionary in the same way as we did before, but in this case we have the dictionary. We add data. Now that adding data, if we look at the data at the results here, just look at that value there. And compare it with what we had, 41 milliseconds, 88 milliseconds, 31 milliseconds, and then 146 milliseconds. So that algorithm to take an unbalanced tree and balance it takes a long time. But then you have the advantage. Look at the searching time. It's very, very quick. Compare it with the others that we had so far, and you will see that it's very, very efficient to have that balanced tree. But the cost is the algorithm to make the thing, to balance it. That's the built-in .NET sorted dictionary class. Next example is when we use a hash table. Now here comes in hash table implementations. And before we do these examples, we just have to go a bit back to theory. Let's go to the theory first before we carry on with the hash table implementations, so that we understand what the hash table is. All right. A hash table is a table of cells, let's say an array. Okay, for example, I have to stay nearby the microphone. Let me just check before I carry on. Can the people online still hear me? Can I just have feedback, please? Thank you, thank you, thank you. That's good. And I believe that is because I'm focusing to standing nearby the microphone. All right. A hash table is an array of cells. It might have a lot of cells, more cells than needed. And then what I do, remember now the idea of a key value pair. Remember the idea of a key value pair, keys and values. So what I do when I want to put in an element in my hash table, I calculate the hash value, or hash code if you want to, based on the key. So there are algorithms or functions or methods or whatever you want to call them to take the key, manipulate it in some way, and get a value. Take that value as the index of the array. So take the key hash code and put it in that specific spot in my array. So let's say I have a hash code algorithm, and I take the word Mike, and I calculate the key value, I get 390. And then I have to use the modulus operator because I may not have enough spots in my array to take each and every index as an individual spot. So take the 390 mod 10, get a 0, and put that Mike entry in space number 0. Take the word Susan, calculate the hash code, get 522, modulus 10 is 2, so put Susan in index 2. Get John, the hash code will return 399, modulus 10 will be 9, put that in spot 9, index 9. So this will be modulus 10 if the array is 10 cells long, and I repeat that. Modulus the number of cells in my array. Modulus the number of cells in my array. So I can have 1,000,000 entries possible that I want to put in my hash table. But if the array is only 10 cells wide, I have to modulus my hash code with 10 and use that result for the index of my hash table. So obviously, and this is where your question comes in, sir, obviously we will have collisions. So I will have another I don't know what it is, something else will calculate value 49, modulus 10 will also be 9, and now I have competition for that spot. Now there's one of two possibilities that we can do. We can either kick out the original one and replace with a new one, or we can ignore the second one and keep the original one. Fact is, we have a problem. And that works well in general. So that's the idea of a hash table. Now, one possibility of a hash method, if we can just say that, one possibility of a hash method is to go look for strings, at least, for strings. We can go look at the UTF values of a character in the UTF table, page 3, 4, 5, 6 in your textbook of last year. There's that table, you remember? Every character has a value in the UTF table. And then add those values, and then you get a total for that key that you can use as your hash code. That's simple. There are other more sophisticated, more complicated methods to calculate the hash value. There's also a built-in method that you can use to calculate the hash code. For every object, there's a hash code built-in method that you can also use. But we don't know what's done behind the scenes. So we prefer to do something that we know what's going on. So we often use this one that says, all right, go add up the numbers from the UTF table, and that will give us the hash code. So we need a way to fix the problem of collisions. But let's just stop here and go to that problem a bit later with one of the later examples. I think I might even discuss that on Wednesday. I don't think I will get there today. So let's go back to our example here. So the .NET dictionary use a hash table in .NET. The background, it uses a hash table. So this dictionary class uses a hash table in the background. And it deals with collisions in the background. We don't know what it does, but it does so. So the add entries method takes the dictionary, takes that dictionary, read the values in the file, add the values to the dictionary key and value separately. And then we have our find in the dictionary. And there are two ways. Actually, there are, I think, of three. I have only two here. So we start the timer and we stop the timer when we add the entries, and then we start the timer again when we find something and we stop the timer. Now, if I want to find something, I can either, this keyboard. I can either do this and comment down that. That will give me a run, it will work, but it will give me a runtime error if the element that I'm looking for is not in the dictionary. So if I want to find something that's not present in the dictionary, line 252 will give me an error. So I cannot do that. But what I do want you to notice from line 252 is the square brackets with the index. So when we access elements in a dictionary, we use a normal indexing structure with square brackets. So notice that. Elements in a dictionary are indexed, and we can index with a string or whatever the type is of the key, with a key element inside the square brackets. But as I mentioned, that will give us an error if the thing is not there, so it will be better to do this. Now this thing returns true I did not bother to handle the false case. I just said carry on. So there's no assignment to a bool, but try get value, returns it true, and it puts the value that key points to in S value. And that's all that I was interested in at this stage. But of course, you can handle a false case. And then if we compare, I think this is, what's it, number 5, I think. Is this number 5? I can't remember. Yes, number 5. Compare the times. Quite quick to add, not too fast, not too slow. So that's a good alternative. A hash table is a good idea. It's a good way of adding data into a data structure and finding the data. So putting data into the hash table, finding an element is quick, both of them. So hash table, until now, this is the best of our possibilities, this hash table idea. Why did I say a hash table is order 1? Why did I say it's constant order, no searching? Because we don't search through the thing. We calculate the hash code and we go there. We just calculate the hash code and we go to that spot in the structure. There's no searching done. Not linear, not binary, no way. We don't compare several values to find a specific element in the structure. We calculate the hash code and we go there. Of course, that calculation of hash code could take time. So yes, that's not totally immediate. It's not immediate because the calculation of the hash code takes a bit of time. But it works. And depending on the hash code method that you have, that could be fast. So we have immediately the access to our data without searching data. So notice this. A hash code access to specific element in a hash table is immediate because we don't search. We calculate the hash code and we go to that spot in the array. We still use an array or a list. You can use either. We still use an array or a list, but we do not search through it. We just go to the spot immediately. So that's the .NET dictionary with the hash table background. And then we have the .NET hash table implementation. They're actually the same thing. I want you to compare that line of code with where is it now? Now I don't find it. But a hash table in .NET takes object, does not take string. So that's the only difference. The only difference between the hash table and the dictionary in .NET. So the hash table class in line 285 and the dictionary class in the previous example. The only difference is in the dictionary we specify the types. But in a hash table, we do not specify the types. We use object for key and value, which will actually mean that when we want to deal with the data later on, we will have to cast. We have to cast. So the data in the .NET hash table takes object, and we have to cast the data when we want to work with it. But further, other than that, it's the same thing. So we can compare the output of 5 and 6. So the object thing is a bit slower to generate, but finding data is actually quicker. Remember that we said that with every run of your program, you might get different answers. You might get different feedback. So it's not to say that we will get the exact same feedback next time. It might be different. And we have to look at orders of magnitude when we compare. Now that is a 10 order, I think, difference. So it might be significant. Those of you having statistics, you know what I mean if I say significant. It's not just an English word that sounds nice in the ears. The word significant has a significant meaning. Anybody here having statistics? Okay, so you know what I mean, Etienne. Yes, significant is a very special word. Don't use it just for the sake of it sounds nice. You have to know what you do when you use the word significant. I have to run this thing several times, many times, 100 times. Write down the data, do a comparison. This will be a typical t-test comparison you can do, and then calculate the significance of each one of these. And then you can say, all right, this one is better than that one. All right, so that's the built-in data structures. That leaves us with two data structures, and how much time do I have? I can start a bit. But that leaves us with two data structures where we do the work ourselves, and we do not use the built-in data structures. Now, of course, why do we want to reinvent the wheel? Because you are mechanics. You're not just drivers of a car. You want to know what's going on inside. You want to understand what's going on inside. We said on Monday that the dictionary is a structure where we have a key and a value pair, or a list of key value pairs. And the list of key value pairs can be represented with a struct, as I had in the example, or you can use the built-in, you can use that entry struct with a key and a value and a constructor, or you can use the built-in key value pair from .NET. That's the same thing. And then in the key value pair, you can also specify the type of the data. In my struct, it is fixed as a string. You can, of course, make it generic. And then also have the class user decide what type you want to put in the data. But the key value pair, we decide what is the data type, and then you can have a list of that. And then in a dictionary, we say that it's an order one search for data. Sorry. We said earlier in the semester that there are several efficiency ways to define efficiency, or the N, or the log N, if you have to search for data. But in a dictionary, we don't search. We go to the item immediately because we know what the key is, and you just find it. Of course, there's a trade-off because you have to calculate the position of the key. And there's a hash function, and that might take time. So it's not really immediate, but at least the search is immediate. You just have the index and you go there. So in a hash table, we have an array of data. We have an array of data. Let's start with this one with no collision detection. There's an array of data. Where is it now? There. It's an entry array. In this case, I initially make provision for 100,000 elements. And then we calculate the hash code. And that hash code will then give us the index. So we assign a value to a specific index in the array. So the elements in the array are not in sequential order. They are not even filling all the cells. Lots of the cells are staying empty because those indexes are not addressed. So you might have an index and then adding another value, and the index might be far away from this one, and then adding another value, and the index will be in between. So it depends what the hash code is, where that specific element will be placed in the array. But there can be lots of cells that are empty. So that's another drawback of hash table, in that we have maybe possible empty space, unused space, lost space. And you can calculate a factor to determine, we refer to it as the load factor. So the higher the load factor, the better, because that means the less empty spaces we have. But the problem is that more than one entry may have the same index. And now it's possible to have elements competing for a spot in the array. And then we have what we refer to as so-called collisions. And we have to now decide, how are we going to deal with the collisions? What are we going to do about the collisions? So on Monday, we showed you some of the built-in structures in .NET. We also showed you the built-in .NET dictionary and the built-in .NET hash table classes. And they're actually the same thing. Both use a hash table in the background. But the dictionary class in .NET, you have to specify the type of data, whereas with the hash table class in .NET, the data type is that of object, meaning that you can put in anything in there. But if you want to work with the data afterward, you have to cast back to the type that you are interested in. So that's done by .NET. So as I said, we must try to understand what's going on underneath and see if we can find out how these hash table thing works. So we did our own hash table here. So let's have a look at how this works. So I have an array. I have a timer that starts and stops, and then in that interval I call the method add entries, and then I can afterward refer back to this ms duration property of my timer so that I can see how long did it take for the add entries to be done. So if we go to this add entries method, it is reading a file, and you should not have any problems in reading files, text files. That should be second nature now. Should be able to read a text file. Then in that text file, we have tab separated values, and the first one with index 0 will be the key, and the second one with index 1 will be the value. Those are lines 362 and 363. And then we use the key and we calculate the hash code. So we go again to another method, get hash code. Take the key as a parameter, go calculate the hash code, comes back with an int value. Take that int value as the index in my entries array. And then place my new entry, calling the constructor, in that place. So my hash code or get hash code method there are many possibilities. There's even a built-in one of the object class. But what we do here, since it's a string, we step through the characters in the string, converting every character to an int, and then add all characters together so that we're making use of the UTF table and the values of the characters in the UTF table, end up with a hash code. That's not the final hash code, because the hash code index may of course not be larger than the size of the array. And if your array has a limited number of spots and that hash code value is larger than that, then again we have a problem. So what we do is we modulus the hash code value with n being the size of the array. It's called from there, and that's the size of the array. And then we have an hash code that we can return, so that will then be the index. And we showed you the example on Monday. Let's just go there quickly again. There. If, for example, we have a very simple small array and the array contains only 10 elements, then hash code modulus 10, you can work with the remainder after division of 10. That's the last digit in the hash code. Original hash code will give you a new hash code. That will then be the index in the array. So we need to modulus with the array length to ensure that we don't exceed the array size. And once we have done that, we have now that specific value assigned to a spot in the array with that index. When we want to find the data, again, you have to now calculate the hash code of whatever we are searching for. And again, that get hash code method will take that search key as well as the length of the array, get the index, and then we return the value. So there's no searching done. There's no searching done. No binary search, no sequential search, not at all. Calculate the hash code and we go there. So there's no searching done when we find an element. So if I run this, I want you to look at the output, specifically of the second last set of outputs, which will be my cell phones are busy this afternoon. So look at that set of data there. We know that there were, what was it, 13,000 something entries in the file, but only 1,450 spots were filled. And then the translation for Pieperig is take away. Afrikaans-speaking people will know that that is nonsense. And that is because of the way in which collisions are dealt with. So in this specific case, we had more than one entry getting the same hash code, and then the previous entry was kicked out, replaced with a new one. So takeaway takes the same spot in the array as the English for Pieperig. So that's a problem. So it's actually not acceptable. It's even less not attending class. It's not acceptable. We cannot work with this. But it helps us to understand the basics of how hash tables work. So we have to make provision for collision detection. And that we do in the next example. So what we do in collision detection, I think it will be easier to go to the document here. The principle of how we handle collision detection is by having an array inside an array. Yeah. So you know what a jagged array is. You discussed the jagged arrays last year. It's an array within an array. It's two-dimensional, but it is not really a two-dimensional array. It's not really declared as a two-dimensional array in that it's not a rectangular block. We have an array in the top line, and they are indexed from 0 to 9 in this example case. And then each one of these indexes have another array inside it. Let's take position 3. So there's a spot in my array, but this one in itself has an array. So there's an array inside an array, but all the inner arrays are not of the same length. Even this one with index 0, there's nothing in it. There's no elements with, index 1. No elements with index 1. So in this case, when we get a collision, I don't kick out the original one. I expand the inner array and make space for it. So now I have array inside an array. And then when we want to find a value, we calculate the hash code and go to the index of the outer array immediately. Once we have that index, we do sequential, or maybe if you want to, a binary search, but you have to do a search within the inner array. Right? But it's much faster because you get now the index, and that smaller array in the inner array is very much smaller. So searching through it will be much faster. Got the idea? Now we don't have collisions. When we have elements with the same index, we just expand the inner array and make space for it in the inner array, so that we can put the element in there. Right, so let's have a look at how this thing works in code. All right, make sure that we now declare our entries array correctly as a jagged array. Note it is not declared with a comma. It is not two-dimensional in the real sense of the word, with a rectangular and all the outer index values have the same number of inner spaces. And then we create 10,000 elements. Is it 10,000? Yes, 10,000 elements in the outer array. Step through all the elements in the outer array and create an empty array in the inner array. So the inner array is now empty, but it's there. It's not null, it's instantiated. If you don't do that, we'll get a null entry, a null error when you try to put in data there, because that inner thing must be instantiated as well. So create the outer one, and then for each cell in the outer array, create the inner array. Got that? And then when I want to add entries, again, start and stop the timer, go to the add entries method. This thing reads the file, calculate the hash code, normal way. Now, once I get there, I will have now to expand my array to make space for it. So we will have to resize our array. So an array with a specific, the inner array with the index of the hash code must now be expanded. So it gets the value of k, where k in the previous line takes the initial size and adds 1. And then my entry is assigned with this thing there. This looks like two-dimensional there. So this is the outer array index, and within the outer array index, I use index k minus 1. K is the number of elements in my inner array, and of course, the last index in that array will be k minus 1. And then I create my new entry and I put it in that spot. So this is then a two-dimensional array, and I can put my element there. This part there at the bottom, that's actually not necessary. It's not part of our normal add entries. This is just for the sake of debugging and count the number of valid entries that we do. You can leave that out. But we use that in our output to show that we have placed all the entries that should be placed there have a spot. That's what we use that last part for. But it's actually not part of the placement of the element in the array. So what's left then is to show how we search through this thing. So we have done now the add entries. Now if I want to find a value, I want to find that thing. Calculate the hash code, but that will give me the hash code of the outer array. And remember, entries hash code is an array in itself. Right? This thing is two-dimensional. The whole entry structure is two-dimensional. So if I refer only to the first index, there's still an array in there. Entries hash code is another array. And now, then I can search through that inner array in a normal, in this case here we do a sequential loop. We just search through that, compare. If we found it, it's found. And then once we found it, we refer to that specific spot again with a two-dimensional index. The hash code is the outer array's index. And then I, whatever I is, as we've stepped through it sequentially, will be the spot in the inner array where that element is. And then we're done. Then we got the element. We made use in this hash table example of an array within an array, but you're not limited to use an array within an array. You can use lists, a list within a list. You can use a list within an array. You can use an array within a list. Several possibilities of structures that you can use for the two nested structures. And in the document, the last section, I think, in the tutorial says exactly that you can make use of other structures. And there I have gave you an example of other possible structures. So this is a list of arrays. That one is an array of lists, and this one is a list within a list that you can also use for your jagged for your hash table structure. And it might be a good exercise to go implement them and change the example that I've given in the tutorial to make use of one of these rather. It's not necessarily that you have an array within an array. Let's compare all these data structures and look at that table that we have there. We discussed the first few on Monday, the built-in structures, and also the .NET dictionary and hash table structures, which are using hash tables, and then our own hash table without collision detection and with collision detection. And the two columns there, how long does it take to create the structure and how long does it take to find a value. Now, just those of you having statistics, you will know that that is not zero. It looks like zero. The data is rounded decimal digits, but they may be digits after that. So what's important to us to note is in whatever format you use them are always, if you look at both the creation of the structure and the finding of data, always you get better response. Of course, having it without collision detection is not an option. We just show you here what the effect is, but we never go without collision detection. It's just not sensible to do so because you lose data. I got a question on Monday who asked, why, sir, is one of the things don't enter all the values? Who asked that? Did you have your answer now? All right. So it's not an option.